Alright, in this video or following videos, we might need more because there are a few things here. We're going to see how stationary waves can be formed on different situations. So number one is that you can use a stretch string. Number two is that you can use air column, either closed pipe or open pipe. Closed means one end closed. Okay, open pipe means both end open. And then probably we can also use microwave to demonstrate the stationary wave. Okay, so we're going to go through all this. Yeah, so let's look at the first one, stationary waves on a stretch string. So what you need first is you need to set up the string, okay, one side to the vibrator, and this side to the vibrator, and the other side we let it to be make taut by a weight that is hang down from a pulley. Okay, so at first it's just a straight line like that. Okay, so firstly we turn on the frequency generator. So frequency generator will cause the vibrator here, this tip here, to move up and down. Okay, so as it moves up and down, it will send the wave to the string, and then you get reflected. Remember the incident and the reflected wave, as they interfere or overlaps, they actually give you the stationary wave. And remember I said it must be a certain condition, okay, at a particular frequency, then only you can detect the stationary wave. Okay, so so slowly you turn that frequency generator, and then you can see that one small loop will start to appear. So it starts with a small insignificant loop like this, and then as you turn the frequency generator frequency a bit higher and higher and higher slowly, then you can see that this one actually will get larger, okay. So at one point you can see that significantly, you know that okay, this is a stationary wave of a fundamental mode. Okay, stationary wave of a fundamental mode. So note about the terms that I use here, the fundamental mode. So as you continue to increase the frequency, you can see that the magnitude of this vibration of the loop will get smaller again. Okay, and then you get very messy again. Okay, so that's where you can decide that okay, let's say at this frequency of 50 hertz, okay, you try to change to 60 hertz, and then it die down at 30 hertz, it haven't formed significantly yet. Then you can say that okay, at 50 hertz, that's the frequency of this fundamental mode. All right, okay. So then you can see a big loop like this from one end to one end, and this is the node, and this is the other node, and there will be one antinode that is moving significantly big at the middle there. Okay, so then we record down the frequency. Okay, fundamental mode, and then there's another term that I want to introduce to you that's called the first harmonic. Alright, first harmonic is the same as fundamental mode in this case. So the second thing, as you keep on increasing the frequency, right, then at a certain frequency, you start to see that two loops now appear, just like the picture in B here. You see that okay, now there are two loops. Okay, and then you slowly increase the frequency, then you get larger and larger, and then you keep on increasing again, to a certain extent. You can see that it dies down, and then it becomes very messy. All right, so then you can decide that which one is the frequency for the first overtone. So first overtone is called the second harmonic. Okay, sometimes this groups of the term will be confusing. You try to get used to that. Okay, there are two sets of terms. On the one on the left hand side here, the mode. The one on the right hand side here, the harmonic. Okay, so usually we use harmonic. All right, so just to let you know, there's another second term, which is the overtone mode. Okay, so then you continue to increase the frequency again. Okay, now you can anticipate that. Now then we will see three loops, and then you keep on increasing, you see 4 loops and then 5 loops, but there's a maximum of it. Depends on the tension in the string there, but we're not going to talk about that. So as that go on, then the next one will be called the third harmonic. So which means that this kind of harmonic situation, right, it only can be formed at a particular frequency. All right, at a particular frequency, and it's going to be affected by also the tension in the string. Okay, right, let's move on to the next one. Excuse me. This one, like what I said just now, is a man sitting there is trying to oscillate a string. That's a bird eye view, top view, and then you vibrate it with a particular frequency, then you should see a different pattern here. Okay, so the one on the left hand side here, first harmonic, second harmonic, the third, the fourth harmonic, and so on. All right. Okay, now we move on to another one. It's called the closed pipe. Okay, closed pipe. For closed pipe, the waveform or the pattern of the harmonic is slightly different. Okay, let's notice the difference here. So that's this one shown in the red color line here. This one is actually the pattern of the fundamental mode. Okay, this is called the fundamental mode. All right. Okay, so if you successfully got this by increasing the frequency from a very low frequency, let's say it's a frequency generator here, then you will get fundamental mode. But if you use a frequency that's too high at this length, then you might get the second harmonic. Okay, you might get this in this length here, so you might get this at this length. Okay, or you might get a higher one with more loops inside there. All right, so that's what we don't want. I will explain a bit on that later. Yeah? So now we will start off with the smallest length above the tube, so that is we are getting the fundamental mode. Then we can say that, okay, now the waveform for this is like that. Okay, why I want to emphasize on this is that because this experiment is usually used to determine the speed of the sound. Later we have a video on that. Okay, so maximum amplitude will be at the open end. That's what I say here just now. This is the pattern, right? So it will be going to have the anti-note here, and then this point here will be the note. Okay, sorry, anti-note, and then because the air cannot move at the end there, so it will be always at the note. Okay, I mean that point will be always a note. All right, so it will be always anti-note and note. So as you raise the tube higher, then the length of the air available in the column just now will now increase. All right, then again you will hear a stationary form. You hear a stationary wave form inside there. From hearing sound, you can decide that, okay, again the stationary wave is formed. Okay, how to go about that? Hold on, right? Because we say that if you want to hear a loud sound, here I mentioned that if you want to hear if you achieve the harmonic mode or the fundamental mode of first harmonic, okay, then you should hear a loud sound. Okay, when you place the tuning fork here, tuning fork itself is vibrating at a very soft sound like that. Okay, each of them has a particular frequency. So if you place it at the correct length above like this, then you hear like oh. So that concept is called resonance, but we are not really going to go into details. But this resonance, it resonates the air, and therefore it vibrate greatly, just like the strings now vibrate like that. So the air also is like vibrating along the transfer of the wave, right? So when they vibrate greatly means that it's like your diaphragm of the speaker, as you turn it louder or greater volume, then they vibrate greater, and therefore you hear a louder sound, right? So that's the same idea here. When you are able to resonate the air at a great amplitude, then they will give you a loud sound. So but the moment you detect a loud sound, that's where the harmonic mode is achieved. Okay, so try to understand what I say. Yeah. So then we look at the experiment. So this experiment actually is to determine the speed of the sound. There'll be a couple of things that you need, okay, because we can't use the lab and I can't find really a simulation online, so we're going to just look at this video here. Yeah, hold on, you can fast forward a bit. Okay, so you have a tube set up here. This one actually is a cylinder with some water inside there. Then you place a hollow tube, you put it inside the water, okay, as low as possible, and leave some empty space up there, and then you place the tuning fork on top of it. Then you try to detect some sound, loud sound, not it's like okay. Alright, so this guy is trying to find that point where the fundamental mode is achieved. So he's trying to place it there and then try to detect the sound, and then they say that the sound is rather soft, and then keep on increasing that a bit slowly, and then finally at this about 19 here, then it detect a loud sound. Okay, hopefully you can hear the audio inside there, because I'm recording so I can't hear that. Okay, so finally it hear that sound and then it record down. Alright, this is the length of the tube where the air inside there vibrate greatly and the first harmonic is formed. So then do some calculation here. So lambda, sorry, hold on. Alright, we'll freeze this screen here. Okay, we'll freeze this one here, then I can explain a bit. Okay, so lambda over 4, why is it lambda over 4? Just now remember I said that when you get the first harmonic, right? Can I write here? Okay, so when you get the first harmonic, it's going to be in this form. This is the water level. Okay, so this is actually the lambda over 4. Okay, quarter of a lambda, because the 1 lambda is like this for a stationary wave, right? So it's just showing you this part only. Okay, and therefore it's L plus E. L plus E, what does that mean? Is that E is the N correction. We call N correction. Cannot be too big. The 0.5 is okay. So this N correction, we have to, I'm trying to bring out the pointer. Okay, never mind. So it's 19 plus 0.5. That's what he measured just now. Then from there you can calculate the wavelength as a 0.78, and then frequency that is obtained from the label of the tuning fork. Each of the tuning fork there has a certain label, and then there's 440 in this case here. So you put it into the equation of V equals to F lambda, then you get a 343. Of course you can first do some backward calculation, because we know that the speed of the sound in the air is about 330 to 340, right? So we do some backward calculation, and then you find out that okay, it's about this length. Then we start the experiment at a certain length, then it won't take too much of time. Alright, oops, yeah. Alright, then we come back to this picture here that I mentioned. Okay, so usually we don't just do experiment with one length like this, so we'll move on to increase the lift the tube a bit higher, and then we look for the second sound. And then for the second sound, right now you can say that okay, this one, as you hear the second loud sound, it is basically 3 over 4 of the wavelength is L2. Okay, so we plus the N correction, so N correction C. Okay, so just now is a plus an N correction, now it's plus another N correction. Then from these two simultaneous equation, the speed of the wave that we get will be a bit more accurate. Okay, so I'll end this video and we'll look at the next one in the next video.